So the next level is 1/4 of this, and it's getting larger because remember the number is negative. You put it all together, and here's the different energy levels. 0.053, 0.212, these are the different radii that are allowed. Here's the different speeds that are allowed. Here's the different energy levels that are allowed. This is all for hydrogen. So we should take a second and think about it. We looked at it with what we had, which was classical physics, and then just threw on the constraint of you can only have certain wavelengths based on the path. You know, it was just a complete guess when they did it, but it turns out it worked. And this is the results of it. And it's been proven by experiment this is actually what's going on here. Okay? Good. So lots of theoretical physics going on in the early 1900s. Okay? You could also only have certain angular momentum numbers. So angular momentum is mvr, if you think about a particle going around in a circle. Same thing that we had before. This is what you saw before. 2 pi r is n times the wavelength. H over mv is the wavelength. Put it all together, between here and here, you can only have certain values of angular momentum. N times h bar. Okay, so energy, speed, distance from the center, and angular momentum. That's what L is, angular momentum. All are quantized. You can only have certain values. Okay? So we can go back to the Balmer series in just a minute. It turns out the Balmer series is actually all these transitions when you're dropping down to 2 in the emission spectrum. So when you go from 3 to 2, 4 to 2, 5 to 2, etc., this is where the Balmer series is actually going to be from. Going down to the ground state is a different series. Okay. We've done this before also in chapter 28. The frequency of the photon, difference in energy level divided by h. Okay. Yeah, here, let me show you what I did a little earlier. What you have here is true. This comes from just looking at the difference in energy levels and what you'd expect for the wavelength. And this number is the same thing that you get for the Balmer series. But this is what I came up with. Okay, so here's the nth energy, minus 13.6 eV over n squared. We've seen that. Now if you just write it in terms of m, minus 13.6 eV over m, we want to look at the difference of energy when you go from n to m. So n is higher, m is lower. Difference in energy, hc over the wavelength. Okay? Just to keep the notation the same as they have. You know, solve for the wavelength in the formula. hc over the wavelength is the difference in energy. So put the difference in energy over on this side, put the wavelength on that side, and you get this. So the wavelength, when you go from n to m, is hc over nth minus mth energy level. I'm going to use my favorite 1240 eV nanometers for h times c. Now the nth energy level is minus 13.6 eV over n squared. This one is minus 13.6 eV over m squared. Then when you actually do the math, 1240 divided by 13.6, you get about 21.1. So that's where this number is actually coming from. They don't really do a great job of explaining that in the chapter, I don't think. But it really comes from just subtracting the n minus mth energy levels. So where does the minus sign go? Well, the minus sign is distributed through here. Now it's m squared minus n squared. Before it was n squared minus m squared. So Balmer didn't know any of this stuff about energy transitions. He didn't know the ground state was minus 13.6. the upper levels were 13.6 divided by n squared. None of that. He just had the data, came up with this formula just by looking at the data. What you just saw here is the physics part behind it. So all his theories were the transitions down to n is equal to 2 for hydrogen. That's what he was saying. Okay, good. This is actually called the, oh, you can't see it. So Balmer series, you're going down to 2. Something called the Lyman series, you go down to 1. Ultraviolet, we can't see it with our eyes, though. Okay, good. So this formula for hydrogen predicts what the wavelength will be. This is just 91.9, M and N. Okay, works out great. All based on this energy level idea. So when astronomers look at distant galaxies, they find this light has been strongly absorbed at the wavelength of the 1 to 2 transition in the Lyman series of hydrogen. You can't see that on Earth. You've got to have some kind of space telescope to do this, because ultraviolet doesn't make its way down here to the surface. So this absorption tells us that interstellar space is filled with vast clouds of hydrogen left over from the Big Bang. You know, light is coming in, going through the cloud. Certain wavelengths are absorbed, and that's what makes its way closer to us, and our space telescopes could pick this stuff up. What is the wavelength of the 1 to 2 absorption in hydrogen? Okay, so we can use this formula that we just came up with. So 91.1 nanometers, that's just in the formula. This is N to M, so 1 to 2, you get 122 nanometers. Okay, good. So it corresponds to hydrogen down in the Lyman series. Far into the ultraviolet, can't see it on the surface. We need space telescopes for this. Oh, so first widely used in the 70s. So this stuff is pretty new, right? A lot of this stuff. It's neat when it all falls together, you know. So a lot of people that work, not a lot I shouldn't say, but some people that work in astronomy are also really interested in particle physics, different things like that. It's because there's this huge overlap between all this stuff. Okay, don't really have time to start a whole new section, but if you have time, go through this 29.5. This deals with all these different quantum numbers. Let me see first. We got about 4 minutes. Are you up for it? We've come this far, right? It's 15 weeks into the semester. What's 5 more minutes? Okay, good. So there's some principal quantum numbers. This is all dealing with hydrogen. So this is called the principal quantum number n. You could have only certain energies. It turns out you can only have certain angular momentum numbers too. There's something called the orbital quantum number called little l. Now little l has to be smaller than n. It's all the way from n minus 1 down to 0. So for example, if n is 2, l can be 1 or 0. If n is 3, l could be 2, 1, or 0. It's always got to be less than n, and it could be all the way down to 0. So an n could has more than one l. You know, it's just as I said. This is called the orbital number. There's the magnetic quantum number. So it depends on what L is. So if L is 3, this could be 3, 2, 1, 0, -1, -2, -3. So this magnetic quantum number varies like this. So they all kind of depend on each other. You start with N, then you could figure out what L is. And once you figure out L, then you know what M could possibly be. And then there's something called spin, which is plus or minus a half attached to each state. So this is the spin quantum number, called spin up or spin down. So each state is described by these 4 numbers. Each state will have an N, an L, an M, and then an M sub S. So here it says list all the possible states of hydrogen that have energy -3.4. So negative 3.4, you can either look at the table and know what n is, or you could use this formula to figure out n. This means n is 2. That means L can be 1 or 0. When L is 1, M could be 1, 0, or negative 1, and each of those has a plus or minus half. I think on the next table or next screen there might be a picture of all of this. Yeah. So these are the 8 possible states. So when n is 2, I guess I would start down here. When n is 2, L could be 1. When L is 1, M could be 1, 0, or negative 1. And each of these is got a plus half. Each of these 3 or a minus half. Now when n is 2, L could also be 0. When L is 0, M is 0, and then each of those has a plus or minus half. So we've got 8 different states here. So if you think about chemistry again, there was a way shells filled up. Like you get 2 in the ground state and you get 6 in the next one. These are like the S shell. Here's the 2. This is the S shell. When L is equal to 0, that's called the S shell. Okay, so when L is 0, this is the S shell, and you get 2 states, right? You could put 2 electrons in that shell. When you had the P state, that corresponds to L being 1, and then you saw there's 6 there, right? Go back. 1, 2, 3, 4, 5, 6. I don't know what grade I was in when we did these this hydrogen model filling up shell idea, but I had no idea it corresponded to this. They just tell you S shell there's 2, and that's just the way it is. But really, it comes from this. The P shell, you get 6. Well, they just tell you that, but really, this is where it's coming from. So when you have P, that means L is equal to 1. When you get up to D, that means L is equal to 2. So then M is 2, 1, 0, negative 1, negative 2. Each of those has plus or minus a half. So you could add all those up as well. Okay, so I wanted to show you this because it's really the combination of quantum mechanics from physics and chemistry and how shells are filling up. Okay. Any questions on that? We'll leave it with that for today then. So all this chapter 29 is just bonus stuff. Take a look at the bonus homework set. It basically deals with what we've done today then. All right. Excellent.